All right, everyone, welcome back to the EECS 370 discussion. Today we'll be going over combinational logic, which should hopefully be most of your view from EECS 270 and 203, whichever one you've taken. Today we won't just be talking about the math stuff, we'll also be talking about how we actually implement these things in hardware. And so we're going to use this knowledge to build our LC2K processor over the next couple of weeks. So here we go. First, I want to go over the upcoming assignments. This semester, all of our projects will be due on Thursdays. And because the first two projects are broken up into parts, that means that for each of the Thursdays between now and spring break, we will have some sort of project due that night. So don't get behind. That's going to be really costly. Also, we're going to have our homeworks due on Mondays this semester, except for the last two homeworks. Those are group homeworks, and we're going to give you time to work in groups in your discussion section for those last two homeworks. And so we'll actually make those due on Tuesdays instead of Mondays, so that you have a little bit of time after your Monday discussion to finish those up. Otherwise, from now till spring break, a project piece due every Thursday, and then we have homeworks due on 2 of those Mondays. Speaking of projects, make sure to start early on them. This graph is from just the other day when project 1A was due. This graph shows you your final score versus the first submission time. So let's see. So project 1A was due the night of January 27th, so right about here. And so if we track back 3 days about to, let's say, the end, I guess, of the 24th, we will see that's when the scores start to dip. So if you made your first submit more than 3 days before the product was due, you have at least like an 83. But if you submitted your first submit after the, I guess, the 24th, then there wasn't really a guarantee on what your final score would be. So we're going to see the same trend with Project S, I would assume. Here's that same graph from the Project 1S students from last semester. I guess at that point, the due date was September 23rd. And so, of course, all these people on the right of that date are using their late days. We already can see a couple over here from Project 1A. But all that is to say that starting late on the projects is going to be costly. So don't do that. And especially with all the projects being due back to back this term, that's going to be really difficult. So like I said, today we're going over combinational logic. Now, combinational logic is basically math implemented in hardware. A bunch of logical statements that are going to be true all the time. But we're also going to have to introduce sequential logic in order to sort of save our state. Because if we're trying to solve a problem and we do it with just combinational logic, we're going to be needing a whole lot of hardware to get our final answer. But if we're able to save outputs at certain times and feed them back into our inputs, then we'll be able to reuse the hardware. It might take more time, or it might take about the same amount of time, depending. But we will be able to reuse that, lower our costs, and make machines that aren't so problem specific. And so that's kind of the motivation there. But first, we'll go over all the combinational logic that will serve as the basis for the sequential logic. And then those two things combined will serve as the basis for our finite state machines. So to start us off, all of our combinational logic is going to be based off of gates. And our gates are going to be pretty much exactly our operators from EECS 270 and 203, all of our logical operators. So you might remember the truth tables. We're going to have a gate based off each of the truth tables. And so that means that each of the operators that we use in 203 and 270 will have an equivalent gate. So let's look. I guess before we go into the hardware, I want to remind you of this analogy. We can think of our computers as working off a bunch of light switches as inputs, and then the outputs being a whole bunch of light bulbs. So if we just have a wire that connects our light switch and our light bulb, whenever the switch is on, then our light bulb is on. And whenever the switch is off, our light bulb is off. And so we can modify that behavior with a bunch of gates. So for a high voltage, we're going to call that on, or a 1, or a true, generally in the 1.2 to 1.8 volt range. And then when our switch is off, we're expecting a low voltage, so we'll call that 0 or false. And we're expecting that to be between 0 and 0.6 volts. Sometimes we do have some voltage leak in the 0.6 to 1.2 volt range. And we're going to generally label that as an X, as in we know that that's supposed to be something, but something's gone wrong with our hardware. We don't know what it's actually supposed to be. But for the purposes of 370, I wouldn't worry too much about the X's. Instead, we're going to deal with 1s and 0s all the time. So let's see. So let's look at our 3 basic gates with their truth tables. So first we have the NOT gate, which is just going to invert whatever the input is. So if our light switch is on, then our light bulb will actually be off. And then if our light switch is off, our light bulb will actually be on. OR gates are going to have their light bulbs as on whenever either of the 2 input light switches are on. And then the light bulb will only ever be off when both light switches are off. And so if we think about some sort of even distribution of inputs or light switches, we're going to see that about 25% of the time our light bulb will be off, and about 75% of the time the light bulb will be on. Looking at the truth table here, we have 1/4 of them being 1s and 1/4 being 0s and 3/4 being 1s. And then our AND gate will be flipped. The light bulb associated with an AND gate will only be on when both of the light switches are on. So again, with an even distribution, we're going to have our light bulb be off 75% of the time, and our light bulb be on 25% of the time. Now, just for fun, we've shown you how these can be implemented with transistors. You might have seen some of this in 270. I think this is more heavily touched on in 216, which I've not taken. I kind of breezed over it when I took 270. So I don't know too much about this, and we're not going to worry about that for this class. But if you want to look it up, it's called CMOS or transistor circuits, and it can be some pretty cool stuff. We're also going to use a couple other gates in EX370. We know that we've been using this NOR instruction in LC2K. We're also going to have a NOR gate, and a NOR is just an OR with a NOT afterwards. Similarly, a NAND is just an AND with a NOT afterwards. We also have XOR, which is a gate that's going to tell us whether 2 inputs are distinct. So an XOR will only be true if either A is 0 and B is 1, or A is 1 and B is 0. And then we can also make an XNOR gate by putting a NOT after the XNOR, and that's going to tell us if 2 inputs are the same. So there'll only be a 1 from the XOR if both A and B are 0, or both A and B are 1s. And so these are going to be the regular gates that we're going to see in EX370. Now, a couple things to note. Our AND and OR operations are commutative with their own things and associative. So just like addition and multiplication, which are both commutative and associative, not with each other, with their own operations. The AND is going to be commutative and associative, and the OR is going to be commutative and associative. And that's because the OR operation actually functions sort of similar to an AND operation, the addition operation. And an AND operation is going to function similar to multiplication. To hear more about that Boolean algebra stuff, you can look it up or go take 270 if you haven't already. But that's going to allow us to sort of combine gates sometimes. We have 3 inputs that we're ANDing all together. Instead of making separate gates, we can combine them into 1 gate. So for example, this circuit over here, the circuit A, really represents this, where we're doing the A and B first, and then we're feeding that into another AND operation. So this is equivalent to A and B and C, if the B and C are in parentheses. All the same thing, very useful to us. So after looking at that, let's go to our first problem here. So we have some logic gates for you here, And I would highly recommend memorizing what these look like. So if you see this kind of block-shaped D gate, that's going to be an AND. And when we see the crescent curved one, that's going to be an OR. And anytime we see a little bubble, that's going to be a NOT gate. So I'll mark that as NOT. And so whenever we're turning these into a logical equation, we can generally work from the back towards the front. I guess you could also work from the front towards the back, but I think the latter or the former will be easier. So let's look at this here. So we have an AND gate at the end. So we have some output F. We will assign F to A and something. So we'll have a NOT. So we'll go ahead and put the NOT there. And then I'll put something else in parentheses. Then we have an OR gate. B is the first input to the OR. And then NOT C is the second input to the OR. So this is how we might write it in bitwise C or C++ form. We also here have the logical C or C++ form, and this should be a double AND actually to do the Boolean operations. I guess on the homeworks and things, you can also do whatever we did in 203 and 270. Like I think maybe this was an XOR. Maybe this was a NOT. I can't remember. It's been a while since I've taken both those classes. So, but whichever one you use, that's fine. But this would be our answer for this question. One thing I do want to know, if we go back real quick, I said that the bubble, anytime we see the bubble, that's going to be a NOT of some sort. And so before we get to the next question, I want to remind you of De Morgan's law. De Morgan's law says you can take a NOT on the outside of an OR or an and you can sort of distribute it. And so when you distribute it, you turn the NORs, or you turn the NOTs, sorry, you turn the ORs into ANDs, and you turn the ANDs into ORs, and then you NOT both the inputs. So this NOR gate here would be equivalent to an AND gate with knotted inputs, A and B. Similarly, this NAND gate here would be equivalent to an OR gate with knotted inputs, A and B. And so I'm going to use the bubble here to represent a NOT. So anytime you see the NOT, that's going to be a bubble of some sort. All right, so now that we know that, let's move on to problem 2. So in problem 2, we're trying to create an XOR gate just using NAND gates. And so we're going to call NAND gates functionally complete. Just like we showed in the last discussion, you can use the NOR operation in LC2K multiple times to create any other bitwise operation, and that was functionally complete. So NAND gates are the same way. We can take any number of AND gates or NAND gates and turn them into any other gate that we might need. So let's look at this here. By the way, before we get started, we're probably never going to ask you to do this exact question. Most of the time, we'd probably ask you to do 5 NAND gates instead, and we'll see why in just a second. So whenever I'm trying to put some gates together, I'm first going to write out what I need. So if we have an XOR and we're trying to make that out of NAND gates, I'll first write the definition of XOR, which is a 1 whenever the 2 inputs are different. And so either A and not B, or not A and B. That's the definition of XOR. So now I know that we're trying to get to only NAND gates. So that means I'm probably going to want to preserve all the NOTs and ANDs that I see, but I want to turn this OR into a NAND somehow. And so remembering De Morgan's law, I can first double negate and then distribute this negation here to turn the OR into an and to NOT both the inputs. So now we have a couple of NAND gates here and there. So here's one NAND gate. Here's another NAND gate. Here's another NAND gate. And then remember from NOR, if we NOR something with itself, then it's just not the input, because if you do an OR of something with itself, it's just that thing. Similarly, if you do an AND of something with itself, it's just that thing. So when we do a NAND of something with itself, it's just the not of that thing. So not A is equivalent to A NAND A, and not B is equivalent to B NAND B. And so if we were asking you to do this question with 5 complete NAND gates, this would be it. This is we'd have to draw out the diagram, but that would be it. But we're going to take a trick from 203 with our logic rules. We're going to do a little bit of absorption. And again, I would never expect you to recognize this immediately, but we can do some absorption and recognize that we have repetition of not A and B here and here. And then one thing that we can do with our gates that we can't do with our equations is reuse things. And so that blue NAND is going to correspond to the NAND I'm coloring with green here. And so this would be an XOR gate. Now, we would also want you to know how to go the other way. So if we gave you the circuit and asked what regular gate is represented by this circuit, we would expect you to come up with the answer. And so if you wanted to do that, all you would have to do is construct the truth table. So this has 2 inputs. So we'll have our 2 inputs A and B, and our output Q. And so we'll just construct our truth table with 0, 0, 1, 1 for A and 0, 1, 0, 1 for B. And then we would look at our circuit to see what the value of Q would be based on these input values. So let's look at this. So when we have a NAND, anytime one of the inputs is a 0, our output will be a 1. So if we feed the A through this NAND gate, it'll be a 1. If we feed a 0 through this NAND gate, it'll be a 1. And so 1 NAND 1 is 0. So here it would be a 0. Now let's look at this here. So if A is a 0 and B is a 1, so this will stay at 1. This bottom NAND gate will now be a little different. So we have to look at actually this first one in order to figure it out. So A is still 0. So this NAND gate is going to be a 1. B is a 1. So 1 NAND 1 is 0. So here's a 0. Here's a 1. And so because this down here is a 0, this final NAND gate will be a 1. And so our answer will be a 1. Now, noticing that we have some sort of symmetry along this line, we know that A being 1 and B being 0 is equivalent to A being 0 and B being 1. So we'll just paste another 1 there. And then finally, if they're both 1, well, then this down here will be a 0, which will make each of these a 1. And then 1 NAND 1 is 0, like we had at the very beginning. And so then we see that this 0, 1, 1, 0 is an XNOR. And so you would probably need to know how to do that. But yeah, so there's problem 2. So now we've done a lot of the stuff that we've done with the gates. We'll get back to gates in a minute. But before we get to gates, I want to talk about this thing called propagation delay. So we think of everything as a light switch. We can realize that these are voltages. These are traveling through wires of some sort. And voltages and electrons travel at the speed of light, which is finite. It's not infinite. So even if we had a wire going directly from A to Q in this picture, there would still be some amount of time when A is a 1 and Q is a 0. It would be microscopic. The human eye cannot see it, which makes our light switches really, really convenient, of course. But the same thing is going to be true for gates. Because gates have these transistors and wires, our gates are going to have longer delays than our wires. And so in this class, we will give you the delays of the gates. Typically, these are found through experimentation, I guess. But once we construct a bunch of gates and put them in series together, that means that our propagation delay is going to build. So for example, if we have this A that changes voltage, and it takes all of our gates 2 nanoseconds to update based on that voltage. So the A voltage will travel along here and along here at the same time. And so after 2 nanoseconds, that change will be reflected here and here. But then this change will travel along here and take another 2 nanoseconds to be reflected along here. And then finally, it'll take another 2 nanoseconds to finally be reflected in Q. So in total, it takes 6 nanoseconds for a change in A to be reflected in Q. So we wouldn't call it 4 nanoseconds because the change in A isn't just going along this top and final NAND gate. It also has to go through this first one. And it wouldn't be 8 nanoseconds either because a change in A isn't going to go through this bottom NAND gate. And so we're going to call this looking for the longest path. So whenever we have a change in one of our inputs, we can see where the longest path that travel propagation is, and then count up all the delays, and that will be our actual delay for the entire circuit. So let's look at this one here. So typically we'll give you, like I said, the delays for each of our gates. So we have a bunch of gates and we're trying to figure out the propagation delay for the whole circuit. I think the easiest thing to do is to first label all of our gates with their respective delays. So go ahead and do that now. So we have 2 nanoseconds for NAND, 4 nanoseconds for NOR, and 5 nanoseconds for OR. Now, that might seem a little strange to you because isn't a NOR like an OR plus a NOT? Wouldn't a NOR take longer than an OR? And this is just some trivia. In reality, we can actually use our transistors to make NOR gates that are faster than OR gates. So sometimes we might actually construct an OR gate by taking a NOR, just like this, and feeding it through a NOT. That might actually be faster sometimes. So that's actually pretty common. Same for AND. But yeah, that's just some trivia. Anyway, so looking back at our propagation delay, we have, let's see, so we have a bunch of circuits here, or a bunch of gates in our circuit, and we're trying to find the longest path. So let's just go from the top at first. So we look along this top path, a change to this initial NAND gate will take 2 nanoseconds to update here, and then it'll go along, it'll go through this OR gate, take another 5 nanoseconds. So now we're at 7, and then it'll go through this final NAND and take a total of 9 nanoseconds to update. Okay, so our propagation delay might be 9 nanoseconds. Now, if we go along here instead, it'll go through this OR, then it'll go through both this OR and this NOR. So let's take the top one first. So now we're at 5 plus 5, which is 10 nanoseconds. And then it'll go through this final NAND gate to bring us to a total of 12 nanoseconds. Now, if we went through this bottom NOR gate instead, that would be 5 plus 4 plus 2, so 11 nanoseconds. And then if we look at the bottommost path total, change would go through the NOR gate, then this NOR gate, and then the NAND, and take a total of 10 nanoseconds. So the longest out of all of those was 12. And so our actual delay for this circuit here is going to be 12 nanoseconds, the longest path. All right, so let's take a break from that for a minute and look at this thing called timing diagrams. So in this class, we're going to use timing diagrams sort of like graphs, sort of like binary graphs, if you will. And so we're going to have the inputs and their values at all times. And then we're going to show what the output would be at all those times based on the inputs. So if we have a circuit, we're going to take each section of time where the inputs are the same. So for example, here, if we're counting a peak of one of our inputs as a 1 and a valley as a 0. So here, x is 1 and y is 0. Then here, they're both 1. And then here, y is 1 and x is 0. And so for each of those little sections, we'll just do the truth table and then figure out what our output is supposed to be. So 1 and 0 is 0. So f is going to be 0 for this first period of time. Then 1 and 1 is 1. So as y flips to 1, f will also flip to 1. And then here we have 0 and 1, which is 0. So when x goes down to 0, f will also go down to 0. And then that's what our timing diagram would look like. There it is in red, in case you were curious what it looked like in red. But that's our timing diagram. Now, timing diagrams are going to be very useful because they're like graphs. They're showing us what our output value is going to be for all times. But when we add in propagation delay, that's going to shift a little bit. So when we add in some propagation delay, we can just take our output and we can shift it by the propagation delay for a single gate. And we can see how it takes 1 nanosecond for a change in the input to be reflected in the output for either X or Y. Now you have to be careful. If you have a circuit that's more than one gate, you can't just shift the output like this. This is just an example. But you might have scenarios where a change will be reflected in maybe the top path of a circuit before it gets reflected on the bottom path. And so you'll have this amount of time where the output isn't logically correct based on the inputs. That is definitely very possible. So we have to be careful with that. And I guess we'll look at an example in a minute. So getting back to our gates and the things that we can do with them, this first thing that we're going to do is construct a mux, which is also called a multiplexer or a selector of some sort. But we're pretty much always going to call it a mux. So know what the term mux means. So we have our mux. And if we think of our mux as a selector, we're going to have a number of inputs to our mux. And at all times, the output is going to be one of the inputs to the mux. And so we're going to use these selector bits to determine which one we're going to pick. So we'll use our selector almost like an index. So we'll zero index our inputs. So we'll call A 0 and B 1. And so if S is a 0, we'll copy A to the output of the mux. And if S is a 1, we'll copy B to the output of the mux. Pretty simple. And so we can implement it with this circuit here. It has, let's see, it has A and not S, or S and B. And so we can see that S or not S has to be true at all times. One of them has to be true. So that means that when S is a 0, the output of this top AND gate will be exactly A. And when S is a 1, the output of this bottom AND gate will be exactly B. So that means that the inputs to the OR gate will be A and 0, or 0 and B. And so that means that our output will be either A or B. Can't be anything else. One way you could write this in C, C++, or Verilog is with the ternary operator. So we have our selector, some sort of statement that's a Boolean statement. Then we have our value of true and our value of false. You can definitely use this on the projects. If you want to look it up on the internet, it's called the ternary operator, ternary meaning 3, because we have 3 inputs, S, B, and A. But yeah, you can definitely use that in projects, and that simulates a mux, sort of like an if statement. So if S is 1, we have B, else we have A. So let's actually look at the circuit. Let's think for a second about our propagation delays. So we see that the circuit is mostly symmetrical, so our propagation delay isn't going to affect us that much. But we do have this one knot on S that isn't reflected in this bottom AND gate. So let's say that S is switching from 1 to 0. So that change is going to be reflected in this bottom AND gate first. And so if S is switching from a 1 to a 0, the output of this AND gate will go from B to 0. And then that will be reflected in this OR gate, because this is still 0. This is 0 here. And so our output has now gone from B to 0. Then a short while later, once this finally gets to the not, then the and, then the or, it'll switch back to A. So for a brief period of time, our output of our mux is going to be something other than our inputs. And it'll be something similar when S switches from a 0 to a 1, I suppose. It could be some sort of garbled output. But that's how propagation delay could lead to these things called, I think, like variance or deviance. I can't remember the exact word. I might be mixing up my Marvel terms at the moment. But there are these little chunks of time where our output doesn't combinationally match any of our inputs at any time. So we have to be careful for those. And so we're going to add extra delays to other things to account for that. to make sure that by the end, everything propagates through and we get the correct combinational answer. Now I said that we could have any number of inputs for our mux. And so if we want to have a 4 input mux, for example, we're going to construct that with multiple layers of muxes. And so that means that our selector bits have to become multi-bit. And so just use one selector bit for each layer of our mux. So that means if our selector is 1, 0, then we'll pick input number 2, because 1, 0 in binary is 2. And so that's how we would make a multi-bit mux. We also have these things called decoders, which take a binary number and then output a wire to tell us what the binary number is. So for example, if we have 2-bit binary numbers, there's 4 possible inputs. It could be 0, 1, 2, or 3. And so we'll just assign wires to each of those values. So if the input is a 2, then wire number 2 will be a 1, and all the others will be a 0. This is kind of based on the idea that we can do like a constant equality check if we have a number. So if you ever have a binary number, let's say that we have 11, for example. So 11 in binary is 1, 0, 1, 1. If I had 4 bits of input and I wanted to check if it was equivalent to 11, then I could write my 1, 0, 1, 1 sideways and make an AND gate and then connect my wires. And then the output would be a wire telling me whether it was equal to 11. And you can do that for any binary number, kind of cool. But notice here how we have like 0, 0, which is 0. This is kind of reverse. This should be sort of up and down, but we have 0, 1, which is 1, 1, 0, which is 2, and 1, 1, which is 3. We can use that to check equality. And so a decoder is just going to be a bunch of those in sequence altogether, right? Okay. And then finally, we also have this other circuit that we can build. And this is how we're going to do our addition in binary. So you might remember from our discussion, I think last time, how, or maybe it was discussion number 1, where we did binary addition. And if we remember, so if we just add 2 bits together, most of the time we'll just like add them. So this 1 plus 0 would be 1. But if we have 1 plus 1, for example, we're going to put a 0 and carry the 1. And that's going to be 2. And so we're going to take this carry bit here and this sum bit and represent it with gates. So to figure out what gates we need, we can build a truth table, noticing that the only time we need to carry is when both of our inputs are 1s. And then otherwise our sum will be a 0 if we have 0 and 0, a 1 if we have a 0 and a 1, or a 1 and a 0, or a 0 if it's 1, 1. And so looking at these gates, we see a 0, 0, 0, 1, which is an AND gate, and a 0, 1, 1, 0, which is an XOR. And so we can put the AND and the XOR over here, and now we have a 1-bit adder, which we'll call a half adder. Now what about the next bit? So for example, if we had 1, 0 plus 0, 1, have the 1 down here, we'd have some sort of carry bit, which would be a 0, and we'd add all these together, get a 1, I guess. And so now, essentially, when we do our second bit, we're working with our 2 original inputs plus a carry bit. And so now we're going to have a larger truth table to figure out what our output should be. We'll still have a sum bit. We'll still have a carry bit for the next one. And so we can look here and notice that every time we flip one of these 3 inputs, our output is going to flip. So we know it's an XOR gate. And then we know that we have to carry a 1 anytime any 2 of our inputs is a 1. So we'll just have 3 ands to check if A and B, or A and carry, or B and carry is true. And if any of those is true, we'll output a 1 for our carry bit. And so that's how we get a full adder circuit. So that gives us 2-bit addition if we connect this carry here to this carry in over here. Now, if we link a bunch of full adders together, we get multi-bit addition. So this right here is a full adder for 4 bits. And so this right here will typically be a 0 for the carry in on the first one. Or you can just use a half adder instead. Now notice that these signals, if they're starting here from A and B and going through an AND gate and then going through another AND gate and another OR gate, oh, and then this carry is going to go back to another AND and another OR and so on and so on. That means that we're going to have a lot of propagation delay. So when we're doing multi-bit addition, we're going to have like really large propagation delay. It's just going to take a while. And so we'll call this the ripple carry adder because it kind of like ripples along. Anyway, and so once we put 32 of these full adders together, or maybe 31 full adders and 1 half adder, we get a full adder circuit. And remembering that in LC2K, we basically have 2 operations that we need to do. We have addition and we have a bitwise NOR. We can just kind of combine these and then put a mux in front of them to select which one we need at any moment in time. And we're going to call this the ALU, or Arithmetic and Logic Unit. So at all times, these operations are going to be calculated, but depending on what operation we need at any moment, we'll pick between one of the 2 results. So like for an LW or an SW, we still need to do 16-bit addition to know what memory address we're going to be accessing, either to load from or to store to. So we'll use the operation 0, meaning this top input to the mux, the addition, or we might do 1 for our NOR to select which operation we need. So that's our ALU. We also have another little piece of our ALU that we're going to use for BEQ. So we have to know somehow whether 2 numbers are equal. And so remember earlier when I said that for 1 bits, or for 1 bit, you can do an XNOR, and an XNOR will tell you if 2 bits are equivalent. Well, we can feed in our numbers, or 2 inputs, into an XNOR, and then now we have 32 gates telling us whether each bit is equivalent. And then if we do an AND between all of those, that tells us if the whole number is equivalent. And so we'll have this extra wire sticking out of our ALU that will always be calculated. We don't need to select it. And that will tell us if our 2 numbers are equivalent. So that would look something like, so we have like an XNOR on bit 0, an XNOR on bit 1, and so on. And then we would AND it all together. And then our output would be whether or not it's equal. All right. So there's all the gate type of components that we're going to be doing for 370. So just thinking about the implications of these, particularly muxes, because we're going to use muxes all the time. We said that we have multi-bit muxes. So if we have an in input mux, how many control bits do we need? So let's see, let's think, for example, so we had the 2 input mux, which had 1 select line. We had a 4 input mux, which had 2 select lines. I guess if you have a 1 input mux, that's just a wire, and so you don't need any select lines. So recognizing the trend there, if we have n inputs to our mux, we can take the log base 2 of n, take the ceiling of that, like in case we have 3 inputs, we'll just use a 4-bit mux instead, or 4 input mux. And that will tell us the number of select lines. Now, with that in mind, if we have an 8x1 mux, the number of select lines in that will be the log base 2 of 8, which is 3. So LG, which stands for log base 2 of 8, is 3. So we have 3 select lines to an 8x1 mux. And then the number of input lines to an 8 output decoders 3. So that means that for an in input mux and an in output decoder, the number of select lines is going to be equal to the number of input lines. All right. So that's all of our combinational logic. Now we're going to get into sequential logic, which is going to build off our combinational logic. And so the whole idea here is that we need some way to save things temporarily. And we can't do that with combinational logic because it's always just going to propagate through. So we're going to get clever with our circuits and figure out how to do that. And so the first thing that we'll do to implement this is to construct a latch. So we're going to have this thing called a SR latch, which stands for set and reset. So set means set to 1, and reset means reset to 0. And so that means that we're going to have these 2 wires going into our latch. One is a reset wire, one is a set wire. When reset is our 1, then our output is going to be a 0. And when set is a 1, our output will be 1. And otherwise, we will just let it keep its state. So we're going to implement this with 2 NOR gates that feed back into each other. So let's look at the implications here. So if reset and set are 0, then the output, well, if set and reset are 0, then our NOR gates basically turn into NOT gates for the input. And so that means that if we feed this output Q into our NOR, the output will be NOT Q. Similarly, if we feed NOT Q into this NOR up here, we get a Q. And so it's just going to keep going back, and it's going to be logically true the whole time. It won't keep flipping back and forth. Now, once we have a reset as a 1, that means that the result of this NOR gate has to be a 0. That means Q is a 0. And then similarly to before, our 0 is going to propagate through this bottom NOR gate, and NOT Q will be a 1. And then by symmetry, whenever S is a 1, then NOT Q will become a 0, which will in turn make Q into a 1. Now you might be wondering, it looks like there's something missing from our truth table. We only have 3 rows. What about the 4th row? So when we have both set and reset as a 1, that means that both Q and NOT Q will be 0, and that doesn't make sense because they're supposed to be opposites. So we need some way to make sure that we never have a situation where both S and R are 1. And so from that, we're going to construct a D latch. And so a D latch is going to control our set and reset wires. We're going to have this gating signal or enable bit. So if R or S is a 1, that means that G has to be a 1. And if G is a 0, then by this AND gate that we're going to put in, both S and R are going to be 0. It means we never have a situation with both. And then we have our data also, and we're going to have a NOT data going into the reset line and just the data going into the set line. So that means that we will never have a situation where both of these AND gates are 1. So we'll never have a situation where both S and R are 1. Now let's look at this. So when let's assume that G is a 1, so it's enabled. If D is a 0, then this NOT will be a 1. So our AND gate will be a 1. We have a reset. Reset will turn Q into a 0. So that's essentially copied the 0 from D over to Q. And by symmetry, it's the same thing for if D were a 1 down at the bottom. We can look at the timing diagram for this. If we have some enable signal that's constantly going back and forth, we're going to see that no matter what the input data is, it's only going to be copied over when G is a 1. So we're going to have some sort of X state at the beginning. We don't know what it is. It's supposed to be something, can't remember. And so when G turns into a 1, we'll copy over D, which is a 1, down to the bottom. And then if D changes at any time while G is a 1, that change will be reflected. Now again, when G is 0, if D turns into a 1 again, it'll have to wait until G turns into a 1 once again to be reflected in Q. And so while G is a 0, all these changes going up and down will not be reflected at all. It'll just keep whatever it was from before. And so we're going to call this a D latch or data latch, which will make preserving our values really easy. Now, it is kind of, inconvenient, it's kind of inconsistent to have some sort of constant state while G is a 0 and our output may be flipping back and forth while G is a 1. So we're going to want to prevent that with a flip-flop. But before we get to that, let's look at this G signal here. So notice how it's going up and down at sort of a constant rate. Now we're going to call this a clock. And we have these really cool hardware pieces that oscillate voltages for us. And so they'll do that at a pretty constant rate. And so they'll have edges where they're going from 0s to 1s and 1s to 0s. And so we're going to call this a clock made from some sort of oscillator. And so that's going to allow us to control these G inputs really precisely. Now, I mentioned that we need a flip-flop. So to make a flip-flop, we're going to capture 2 of these D latches, and then we're going to string them together and not one of the G inputs. So that means when G is a 1, there will be some sort of constant state. When G is a 0, there will be some sort of constant state. But when G changes, that's when our output is allowed to change. Specifically, when G changes from, let's see, from a 0 to a 1. So we're going to call that the rising edge. We could also make a falling edge triggered flip-flop, but that's less common. So let's look at the timing diagram for this one. So we have data that's just kind of going back and forth, doing its thing. Then we have a very consistent clock. Now, when this clock edge goes high, we see that data is going to be copied to our output. So this 1 here is going to be copied to Q. And then when the clock goes down, there's no change. And so what's happening is that when this clock is high, that means that whatever is going into small d over here is going to get copied to Q. And when the clock is low, whatever is going into big D will be copied into small q. So that means that on this change, we're essentially allowing D, big D, to flow into little q. And then when it goes back up again, it'll latch it and keep that as big Q. So there's a very, very brief moment where D is going to be connected to Q. And it won't even be that direct, but it's still going to have the effect of copying D over to Q. So let's look at this again. So when we have a rising edge here, D is a 0, so that 0 will be copied over. Here's another one, D is a 1, so that will be copied over. And that will allow us to have really precise outputs of Q, which we can connect to other combinational logic to do cool things. Right? And so the main difference between the latch and the flip-flop is that a latch, we're going to call this level sensitive because the output could change whenever the enable is at a level of 1. But the flip-flop is edge triggered, meaning it's only going to change when our enable bit is going from a 0 to a 1. And here our enable bit is going to be our clock. And so you can see the timing diagram here. So here's an example where the latch would change state before the flip-flop does. But at this point on the rising edge, they're going to have the same behavior. All right. So this might actually be the exact same picture that we had 2 slides ago. But let's look again at what our output signal and timing diagram would look like if we're feeding in our data and clock into a flip-flop. So we don't know what it's going to start off with. So I'm going to call this some sort of X uncertainty. But when our clock rises, we just copy over D, which is currently a 1, and hold that until the next rising clock edge. Here D is 0, so we'll go down, boom. Here D is 1, so we'll go up, and boom, and we're done. That's it. Pretty easy. So that's all the main stuff we have for this week. Now we're going to get into more of the finite state machines, which are built off of our combinational and sequential logic. So finite state machines are basically sequences. You can think of them almost like instructions in your C code, or maybe your assembly code, LC2K code. And we're going to have a bunch of states that are each going to do one specific thing. And then based on some inputs, they'll go to a next state of some sort. And so that means that we're going to have a bunch of states. Those states are going to control outputs and be controlled by inputs. Every state machine is going to start at some state. And then in order to go from state to state, we're going to draw a bunch of arrows to tell us where to go next. So we can look at this example on the right. We have 4 states: off, on 1, on 2, on 3. Our transitions are the arrows. Our outputs are denoted by the equal sign. And then our conditions for the transitions are marked on the arrows. So if there's no condition on the arrow, then we're always going to follow that arrow. So this little picture over here, we'll call it a state diagram. And we'll see how we can also use a table to represent a finite state machine. So if we're given some sort of machine and we want to create a finite state machine for it, first, we'll list all of our states. Every operation that we need to do, we will list that state. I find it really useful to either assign binary numbers to it or give it a useful name. And we also need to mark which one is the initial state. After that, we need to make the transitions. What are all the possible state-to-state changes that we need to make? And then after that, we can refine it, make it cleaner, easier to read, cut out some unnecessary states and transitions. So let's keep going here. I said that our finite state machines were built off of our combinational and sequential logic. So the rules for transitioning between states is all going to be combinational, right? So you have, if the current state is state 1 and our current input is a 0, then we're going to go to this state next, or we might go to this other one. So that's all going to be combinational logic, and we're going to control that with this thing called a control ROM, which isn't on the slide, but a control ROM is a set of gates, a set of combinational logic, which is going to control our next state. So it's combinational logic that tells us our next state. And then we need sequential logic to actually move from state to state. So we don't, if it was all combinational logic, then we would propagate all through our states and be done with it, and we might somehow be in like multiple states at the same time, and it wouldn't really make sense. But if we have sequential logic, then we can have like a couple registers, a couple flip-flops that store information about our state, and then we just update that to the next state on every clock cycle. And then our enable bit would be a combination of the clock and that other combinational logic that tells us what our next state is. So that's why finite state machines build off of our combinational and sequential logic. So once again, if we didn't have sequential logic, then we would have probably a series of control ROMs that tell us what our final state would be. But then at the same time, we wouldn't really be able to change the input on every clock cycle. So we also need a little bit of time to flip those light switches, if you will. Which will serve as inputs to tell us what our next state will be. Right. So we're going to have 2 different types of state machines. So we have inputs, we have our states, we have our outputs, and we have our transitions. And we have 2 machines. One of them, called a Moore machine, will calculate combinationally the next state based only on, or sorry, it will output the outputs based only on the current state. So we wouldn't do any sort of logical gates between our input and our output. We would only do the logic gates between our input and current state and our next state, or our current state and our outputs. Then we have Mealy machines, which are more advanced, which could take a combination of our current state and our current input and use that to use some logic gates and determine what our output would be. So Mealy machines are more powerful, and we can kind of combine states for more machines based on the inputs to a Mealy machine. So typically, Mealy machines will have fewer states than more machines. Also, technically, more machines are subsets of Mealy machines. So if we have some output function P that still doesn't really use I, our input, and it just uses S, that'd be a Moore machine. So that means that a Moore machine is a type of Mealy machine, but not all Mealy machines are Moore machines. So let's look at some examples here. So before we get into an exact example, remember that every finite state machine will have our states and our transitions and our inputs and our outputs. So we can see a couple examples here, like if we have a person who does three things. They go to work, they go home, and they sleep. We might have some transitions between those two states of being. So if you're moving from your bed to just walking around your house, we would call that the wake up transition, or vice versa, we would call that the sleep transition. We might go from home to work or home to the BBB by taking the bus. For Pac-Man, you might have some sort of state for the ghosts, where most of the time they're trying to find Pac-Man and change their position. But when Pac-Man eats the power pill, they turn blue and they try to avoid Pac-Man. And then once they actually get eaten by Pac-Man, they have to go back to their home state. So these are some examples, but let's look at some that we can construct. Problem 6, we're going to first make a Mealy FSM for a button activated LED. So if we hold down a button, which is going to be our input, then our light is just going to be on. But otherwise, the light will just blink every third cycle. And so for now, we're going to ignore, we're going to assume that the clock is moving so fast that humans can't really tell. Otherwise, we might like lift our finger from B, and then it would take some delay before it turns off the light. But let's go ahead and make this machine. So it says it's going to blink every third cycle. And so that's going to be a hint to us that we're going to have at least 3 states. So I have 3 states. So first, some sort of wait state number 1, and then some sort of wait state number 2, and then I have a state where it's going to be on. So I'll just call this the on state. And so looking at our transitions, we'll just go sequentially through them. So we'll move from 1 to 2, move from 2 to on, and once it blinks, we'll go back to the beginning. And so if B is pressed, if B is a 1, then our light is going to be on. So if B is 1, then our light is 1. Otherwise, if B is 0, then our light is 0. So we'll just assign L to B. Same for the second state. Otherwise, in our on state, no matter if B is pressed or not, it's going to be on. So we'll just assign our light to a 1. And that would be our Mealy machine for our button. I'm going to go ahead and erase my drawings so that you can see the answer here. You can see the exact same thing, just represented with if-then statements. But notice that they actually move the on state over here because the L is always on here. But it's the same thing. So we can do some moving around that. Now for the next problem, we're going to want to convert this into a Moore machine. And so Now that means that we can't have our output B, or sorry, our output L as some sort of function of our input B. So the easiest way to do this is to take our Mealy machine, and every time there's different behavior based on the input, we'll just split that state into two states. So that means state 0, which always has an output of 1, will stay as it is with an output of 1. But state 1 will get split into two states where the output is a 0 and the output is 1. And the same thing for state 2. So now we have 5 states. So we have our on state. We could then move to any of the original state 1. So I'll call this like state 1 off maybe, and state 1 on. And then we'll also have state 2 off and state 2 on. And so we know that we could go from an on state to our on state. We know we could go from an off state to an off state. And we also know that we only want to be in these on states if B is a 1. So that means we'll just make B as a condition for the transition here, which means that B naught will be a condition for the transition to the off states. Now, what if I'm state 1 and I take, and my finger's on the button and then I take it off? Then I would want the light to turn off, right? So I'm going to create a transition from on to off also, if I'm not pressing the button. And then similarly, I can go from off to on if I'm pressing the button. And then finally from state 2, we'll go back to the beginning. And the last thing I have to do is notate what our output is going to be. So here, L is a 1. Here in the on states, L is a 1. And then here in the off states, of course, L is a 0. And so that would be our Moore machine. So this means if you have a Mealy machine and you're trying to convert it into a Moore machine, you will have at most the number of original states times the possibilities for the inputs. And then you can shave off a bunch of them if they're equivalent or don't exist. So for example, we had 2 possibilities for the button B, 0 and 1, and we had 3 original states in our Moore machine. So we would have at most 6 states for our Moore machine. And so once again, I'll erase what I've done and show you what our pretty example looks like. And there's a couple more explicit operators here to show you what's going on, but it's the same thing. And so that's how we would do a button activated LED finite state machine. Let's see. So we have another example here. We want an output to be a 0, and then we want it to be a 1 3 times. So we can just create another state for each of those bits that repeat. So we have an off state where it's a 0, and then a 1 and a 1 and a 1. And so pretty simple, and it'll just move each time unconditionally on the clock edge. Right. And I think here is actually a very similar question to the one we just did, where it's 3 cycles of on instead or something, but I want to move on. All right. All right, so let's look at this other example. So let's say that we're trying to make a finite state machine for a secure car key. So every key has this unique code, which is going to be this, for example, 1101, which is 11. So it's a secret key that this tiny computer chip is emitting. And we want a finite state machine to check if it's the ID that we're looking for. So we're going to have some sort of wait state. And then when we are told that the key is in the car and trying to turn on the ignition, then we'll move out of the wait state and then start to decode the chip. Otherwise, we'll just keep going back to the wait state. And now this is important because you might have states a lot where they just go back to themselves. They can't go back to themselves unconditionally, or else they're stuck there forever. but you might have some condition where it goes back. And so that's definitely something that we need to do. But once it's finally activated, then it's going to check. Okay, is the first bit a 1? All right, then we can move on. But if it's not, then technically we should move to some sort of fail state for r equals 0. Then we get the next bit. Oh, it's not what we're looking for. Then we would go to a fail state for r equals 0. And then we would check the next bit. Again, if it's not what we're looking for, we go to a fail state. And finally, if it's not what we're looking for, we go to a fail state. And then after a fail state, we might go back to the wait state once again. But that's a simple machine to check if we're receiving a sequence that we're looking for. Okay. I'm going to skip all these. All these we're also going to go over in the EECS 270 review, but I want to get to this last problem. We're trying to do another sequence finite state machine. We're trying to check if the last 4 bits on some input stream were 1, 0, 1, 0, assuming that the rightmost bit is the most recent input. So if we have some I that's constantly going back and forth between things, we want our output to be a 1 only when the last 4 bits have been 1, 0, 1, 0. So we're going to have some sort of state, some sort of initial state. Let's call it state 0, where we have no bits. We haven't received anything. So we'll call this the start state also. And we want to wait until we get the first bit that we're looking for, which is a 1. So if we get that 1, let's move into state 1, for example. And now we haven't received all of 1, 0, 1, 0. So we're still going to have our output as a 0. But if we don't get the bit that we're looking for, then we're just going to stay there. So we'll go to 0. Now, let's say that we've gotten the first bit that we're looking for, this 1. Now we're looking for a 0. So if we're in state 1 and we get a 0, oh, then that's what we want. Let's move on to, let's call it state 2. Now, if we have a 1 and we get another 1, well, we don't necessarily want to go back to the very beginning because we can just reuse this one here to construct another 1, 0, 1, 0. So if we get a 1 at that point, we'll just stay in that state. How about? And we haven't gotten the whole thing yet, so we'll keep our output as a 0. Now, if we have received a 1, 0 and we get a 0, we can't reuse that whatsoever. So at that point, we would have to go all the way back to the beginning with our 0. But then if we get a 1, then now we have the third bit of what we're looking for, and we can move on. So let's call that state 3. And we still haven't received the full thing yet, so we'll give that a 0. Now, if we're in state 3, we have a 1, 0, 1. And so if we get a 0, we've gotten what we're looking for, and we have success. So let's call that state 4. And we'll go ahead, because state 4 success, we'll set our output to a 1. Now, if we get a 1, 0, 1 and then get another 1, once again, we can reuse that 1, go back to what we had originally. And so that means that we would go back to state 1. Now, if we have just a 1, 0, 1, even if we do get a 0, we don't want to, be too soon, count our chickens before they hatch. So we want to keep our output as a 0 until the moment where we get that last 0 and we can turn it to a 1. And so that's our success state, but we're always looking ahead to the next thing. So if we already have a 1, 0, 1, 0 and we get a 1, we know that we can use these last 3 bits for another sequence of 1, 0, 1, 0. So at that point, we would go back to state 3. If we get another 1, but if we get a 0, so that would be 1, 0, 1, 0, 0. We can't reuse this in any way, and so we'll go all the way back to state 0. So that's how we would construct a table from some FSM behavior. And there it is in red, I suppose. Everything's in binary instead. So let's see here. I'll erase some so that you can see that. So a lot of time, because our states are actually going to be encoded in binary, we'll write these in binary as well, but notice that the numbers are all the same. And then finally, for our last thing that we'll do today, we want to take this table and convert it into a diagram. So this is going to be really easy for us because we already have our inputs, outputs, states, and transitions. So we just copy it over. So we have 5 states. We have state 0, state 1, state 2, state 3, state 4, right? And so we know that our output will be 0 most of the time. But when we get to state 4, it'll be a 1. And then now we just have to copy our transitions. So if I is a 0 or not I, we'll go back from state 0 to state 0. So I'm going to denote I with a not I. Then otherwise, if I is a 1, we'll move from 0 to 1. Looking at state 1, if it's a 0, we'll move on to state 2. So if not I, we'll move on to state 2. Otherwise, we'll stay in state 1. Looking at state 2, if I is a 0, if not I, we'll go back to state 0, unfortunately. If I is a 1 in state 2, we'll move on to state 3. In state 3, if I is a 0, so if not I, we'll go to state 4. And otherwise, we will go back to state number 1. So if I, state 1. And then finally, from state 4, if we get a 0, if we get a not I, we'll go back to our start state. Otherwise, we can just kind of go back to state 2 and use some things. Or sorry, state 3, I meant to say. Oh no, well, that doesn't work. Anyway, I'll just show you the picture. So we have all of our states, we have all of our transitions, and going back and forth. And so that's how we would go from our table to our diagram. That's all I have for today. If any of this was confusing, we'll also be covering this in lecture over the next week and a half. And there will be also a dedicated EX270 review session that will be released upcoming. So you'll hear this up to 3 times. And if you're confused beyond that, I'd encourage going to office hours because all of our IAs are capable of explaining these things. So that's all. See you next time. I think next time we're talking about project 2 and how we do functions in assembly. So we'll get back to some more of the software stuff next time. But see you later, everyone.